See, the next talk is correlations between microstructure, superconductivity, and electric conductivity in a lanthanum strontium copper oxide compound, DK Christen.
I want to discuss a few of the systematics we've observed in correlations that involve among the sample processing, the microstructure, and the superconducting and transport properties. These are correlations amongst the processing technique, the microstructure observed by TEM, and some of the transport and superconducting properties. I won't have time to present all of them. Materials were synthesized by Lynn Boatner and Brian Sales. Myself, Jim Thompson, and Stan Sekula made the measurements, and the TEM was done by Steve Pennycook, and these are all for the nominally 37 Kelvin lanthanum strontium copper oxide. Very briefly, the samples are synthesized by a technique that involves dissolving the oxides and then subsequently precipitating them from molten urea in the flow diagram sort of outlined here. The main advantage of this technique is that you have a very good control over and achievement of very fine particle size for the subsequent sintering. The samples were then cold pressed at 1500 psi and sintered for 4 hours in air. They were either quick cooled or slow cooled. Quick cooled being they were pulled out of the furnace. Slow cooled, the furnace was turned off and they were allowed to cool for over a several hour period. Subsequently, some of the samples were then heat treated for 900 C and at 900 C and O2 for 16 hours. Okay. Some of the correlations observed in the electrical resistivity are shown here. The upper curve is for the quick cooled sample, which was found to be single phase by powder diffractometry. The slow cooled sample is 15% some second phase, which we have not completely identified. And the O2 annealed sample is single phase and shows very metallic conductivity, whereas the other two indicate some form of either localized or activated conductivity. The superconducting transition temperature, although you can't see it on this scale, is essentially the same at the midpoint, but the breadth is drastically decreased for the O2 annealed sample to a width of about 1.5 Kelvin complete. Now, keeping in mind this curve, for the quick cooled sample, we find for the microstructure something that indicates the sample is quite defective, consisting of many dislocations and some stacking faults. That's for the upper curve. For the slow cooled sample with the second phase, Steve finds that most of the second phase is present in the form of coherent precipitates, those black streaks, and this sample also has several dislocations and some stacking faults as well. Now, after the O2 anneal at 900, the material essentially becomes perfect in both cases. Single phase, essentially defect-free within the grains, and very straight, perfect grain boundaries with no second phase in the grain boundaries. Okay, these effects can also be correlated with the observed critical current densities. We measured these critical current densities in a manner described earlier by Doug Fenimore by measuring the hysteresis in the magnetization, and for that you also need a characteristic dimension of the sample. But what's interesting here, and perhaps very relevant, is the fact that both the quick-cooled sample, which is single phase but very defective, and the O2 annealed samples, which are single phase with no defects other than the grain boundaries, those critical current densities are very low. The only substantially larger are the critical current densities for the sample that was slow cooled. That's the only sample that contains some significant amount of second phase. So it may turn out that it's important from the point of view of optimizing these materials to systematically introduce some second phase. Finally, I just want to make one brief comment we have subsequently irradiated with neutrons to a rather meager dose of 1.3 times 10 to the 18th this slow-cooled sample, and we've seen an enhancement in the critical current density. However, at this very low dose, we've also seen a significant reduction in TC by about 2.7 Kelvin. These are very preliminary results, but perhaps very relevant. So.
Thank you. The next talk is